Laura is a Royal Society Dorothy Hodgkin Fellow and lecturer at the University of Bristol. While a doctoral student at the Université de Strasbourg, Laura was named a French Young Talent in the 2021 L'Oréal UNESCO for Women in Science Awards. She was also a 2024 recipient of the Maryam Mirzakhani New Frontiers Prize, given to her for advancing our understanding of random hyperbolic surfaces of large genus. Before joining Bristol, she was a postdoctoral researcher at the Max Planck Institute. Her research in spectral geometry on the expansion and spectral properties of random hyperbolic surfaces continues the work of the late Maryam Mirzakhani. We are pleased to welcome Laura and look forward to hearing her talk on what does a typical hyperbolic surface look like.
Hello, everyone. And I'm very grateful to be talking to you all here. And my aim today is going to be to show you a little bit what new exciting developments have happened in my little piece of mathematics. Hopefully, you will see how it connects to many different areas of research, and notably to the presentation that Jens is going to give after mine. But basically, what I want to tell you today is what we think, or know now, a hyperbolic surface looks like typically. So the objects I'm going to talk about are surfaces. So they look like this topologically. The only thing we need to know about them is that they have a genus. So there's a sphere, there's a donut, so genus 1. And then there exist surfaces of higher genus, 2, 3, etc. That's what the objects I'm going to talk about today look like. And I want to talk about the question of surfaces of constant curvature. So you know one very simple example, which is the round sphere, the Earth we live on, which has positive curvature. You know another very simple example, you know the flat torus, which you can obtain by taking a little square, for instance, and identifying opposite sides, and then identifying, once again, opposite sides. So that's what the numbering here is for, telling you which sides to glue to which sides. We're going to talk a bit more about these flat tori, but the thing that I'm interested in mostly in my research are hyperbolic surfaces, which you can't make from flat pieces of paper like this. Instead, you have to take pieces of the hyperbolic plane to make them. So this is a little piece of the hyperbolic plane. It's a little disc, which I made using crochet. The thing that's noticeable here is that as opposed to a sphere or a flat thing, it inflates in all directions. You're very welcome to come and have a look at this at the reception afterwards or at the break. And so these objects are very different, but they're also very hard to visualize. Yeah, I made you this because I'm not really able to make you a nice slide to show you what they look like. One thing which is very cool is that in hyperbolic space, there is one octagon which has all its sides the same length and all its angle pi/4. You can't normally do that, but in hyperbolic geometry, there's space to do that. And I can therefore glue opposite edges of this octagon, and I get a genus 2 surface. But the same way I could have picked something other than a square, I could have picked a rectangle or any parallelogram to make my flat torus. I can also do many other things here and get a lot of different surfaces of genus 2, 3, any genus really. And this gives me a very rich family of surfaces that I can try and study. So this is a good pitch if you're a geometer and you like geometry, not so good pitch so far otherwise. But actually, hyperbolic surfaces, or all these surfaces, are very interesting with many respects. So one of the things you might care about could be dynamics. So for instance, the geodesic flow consists in picking on my object an initial position and direction, and then walking in a straight line. Here on the sphere, it's going to be something very simple. If I walk in my direction on the Earth, I will end up back where I started after a very long time. On the torus, situations are quite interesting. So we have these parallel trajectories which emerge. These systems are what we call integrable. There's preserved quantity, and the motion is restricted to a certain subspace of phase space. And they are quite specific. To the contrary, in hyperbolic geometry, if you think a little bit more about this example, or more simply here, very locally, the surface looks like a saddle. If I have my little guy start here or start a slightly different position, the trajectories explored by this little character will go far away from each other, exponentially fast. For that reason, hyperbolic surfaces are an extremely good model for chaos. So the whole butterfly effect, if I start a little bit from a different initial condition, I get very different results. They're an example of very big families of surfaces which have chaotic behavior, and we can use them to try and understand chaos. And that, I would say, is actually a reason why a good part of the theory of hyperbolic surfaces is motivated by. So today I'm going to talk mostly about hyperbolic surfaces and their geometry and spectral theory. Another aspect you can wonder about is number theory and arithmetics, more these kind of things. Actually, some of the examples of these hyperbolic surfaces are related to the distribution of prime numbers and questions like this. So that's another area that is very interesting. So for instance, noticeably, Selberg's famous 1/4 conjecture is related to problems very close to what I'm going to talk about. Okay, so what I like to do personally is consider the large genus limit. So I'm going to take surfaces with many, many holes, which might seem a little bit strange. But a good motivation, I think, is that we have a formula called the Gauss-Bonnet formula, which tells us that the area of a surface of genus G is always 4 pi times G minus 1. So if you want to think, my problem is I want to take a large scale limit. I want to study surfaces which become larger and larger, and I want to wonder, how do they look like? So for instance, I could try and find interesting examples of such surfaces. I could try and prove bounds on various geometric quantities. And I could try to develop a general description. So say every large surface satisfies X and Y property. That's different things we could try and do in this regime. Unfortunately, it's very hard to visualize hyperbolic surfaces. Already for genus 2 example, it's not super easy. But in particular, in genus going to infinity, it becomes increasingly complicated to get a good image, a good mental representation of what these surfaces would look like. And so my aim is to talk about breakthroughs in this world in the last few years. So the thing is, because I failed to draw you one example in genus 2 very well, it's going to be very difficult to give you an intuition about surfaces. So I will take a little detour and talk about graphs, which actually are surprisingly similar. So I want to talk to you about graphs for a little bit of time. We'll go back to our friends' surfaces afterwards. Here is a graph. So it's just a set of vertices connected by edges. And I want to think about big graphs. The same way I wanted to think about big surfaces, I want to take a large number of vertices. So examples of such graphs which arise in actual life are social graphs, where the vertices are people and the links relationships between them. The Wikipedia graph, where the vertices are Wikipedia pages and the edges links between them. You could do that with the whole internet also. Or the Rubik's Cube graph, where the vertices are the positions of a Rubik's Cube and the edges, the ones which are related by one move. So all of these graphs, they have a very large number of vertices, and you might wonder, what do they look like? Can I represent them, or can I study some quantities on them? A particular setting which will arise for us is the case of regular graphs. So a graph is d-regular if every vertex has the same number of neighbors d. So this is the kind of graph which looks a bit like hyperbolic surfaces. Okay. So I fix an integer d, and now I wonder, what does a big d-regular graph look like? So here I took d equal 4, and I tried to come up with my pen and paper with examples of graphs with large number of vertices, and everyone has 4 neighbors. I can do quite a lot of things, but actually if I try to come up with an example that works for every n, I'm quickly gonna be, sorry, it's not very visible on the slides, unfortunately. So here, every vertex is connected with the 3 closest ones. So if I try to come up with some explicit examples, I might have to come up with examples which look a bit like this, which are a bit cyclic. Here it's a cyclic graph, it's organized on a circle. I could construct other kinds of graphs, but mostly when I try to invent them in my mind, I'm gonna not be able to come up with many examples of explicit constructions. But actually, I can instead ask Python to sample me a random graph and plot it. And we can't see much, unfortunately, but here you can see that a random graph has actually, it's very messy. So this is a random 4 regular graphs with 1,000 vertices, and it's very erratic which are connected to which. It's Erdős in the 60s, which had the idea of, in order to understand better what big graphs look like, to study random graphs and introduce a probabilistic method. And this method in the world of graphs has led to a very good understanding. Okay, so now my aim here is going to be to look at certain quantities, because we can see really very concretely that these 2 graphs are different. They don't look alike at all. So now my question is, how do I prove that difference? And how do I do a quantitative study of large graphs? A first very interesting quantity is the diameter, which is the maximum distance between 2 points, 2 vertices in my graph. On my cyclic example, if I zoom out and I draw the whole graph, we can see that the diameter is n/4, where n is the number of vertices. So it's roughly linear in n, because those 2 points at the ends of the circle are very far apart. Whilst actually, this random graph here has a deceivingly small diameter. It has diameter 6. So Python computed the diameter for me for this specific graph. But when you look at it, it's really hard to see that actually, if I take this point and that point, there's a path of length 6 between those 2. And that's true of any pairs of points in this graph. Generally speaking, random graphs have a logarithmic diameter. So as you increase their size, actually points are really close to one another. So this is the case for social graphs. This is something that is quite popular in popular science, the idea that we are all connected to each other. So the diameter of the social graph would be the people who are furthest away in terms of knowing, people who knows, people who knows, people who. There's some literature about the estimation of the diameter in some concrete examples. So here, for instance, for Wikipedia in 2011, it was estimated that any Wikipedia pages can be connected by 18 clicks out of the 2 million pages. And for the Rubik's Cube, the diameter is actually a very important quantity. It's how many moves do I need to go from any configuration to any configuration, which is called God's number, and was proven to be 20, whilst there's around 10 to the power 19 possibilities. So you can see that these logarithmic behavior appears in the examples of graphs which appear in our lives. So that's one quantity, the diameter, which is quite an interesting one. If you want to go and have a further description of the graph and look at more fine properties, one of the things you can do is to compute the spectrum of the adjacency matrix of the graph. So the adjacency matrix is just a very big matrix with ones and zeros saying who is connected to who, and you can compute its spectrum. In the case of a d regular graph, it's going to be between minus d and d. And there's a very special eigenvalue, D, which will always be present because of the regularity. So these are the numerically computed spectra of both of the graphs before, so the circular one and the random one. You can see that they do not look alike at all. Now the question is, what does it mean to not look alike? And what kind of information can I find to discriminate these two? One of the things that is quite striking on this picture is that on this random graph, we have one eigenvalue, so you can't really see, but there's only one here, which is at exactly 4. And then there's a gap here between the 4 and the rest of the spectrum, whilst here, there's no gap at all. So this quantity, called the spectral gap, is the distance between the trivial eigenvalue D and the rest of the spectrum. And it measures how well connected the graph is. So the gap is equal to 0 if and only if the graph is disconnected. So really, here there's no vertices, no edges between those two sets. And it's going to be small if and only if it's poorly connected. So here, once again, can't see so well, but there's just a couple edges related these two clusters. So the question of the spectral gap, or even the first few eigenvalues, is related to the question of clustering, of grouping my graph in a few groups which are poorly connected from one another. And understanding this quantity tells us how densely connected the graph is. So for instance, if we come back to our real life examples, if my graph was all the computers on this planet and the connections were connections between computers, it tells me how many of these connections might break before there's we separate completely the network. So these quantities are quite important with many regards. They are related to the Cheeger constant, which is the infimum of the number of edges I need to cut to divide my graph into big pieces. So this is kind of an isoperimetric constant. So it's how many scissor cuts do I need to make to cut my graph in 2 big pieces. And so the graphs which have a big spectral gap as opposed to a small one are called expanders because they are very well connected and they have very good dynamical properties. So here, if you think about my little geodesic flow or random walk here, and you get an initial condition here, it's going to take a very long time for the walker to end up on this side. Things with a bottleneck like this do not mix very well. And to the contrary, expanders mix very well. So the geodesic flow or random walk here go very well, very fast to equilibrium. Okay, however, it's very difficult to find examples of well-connected graphs. So there are a few number theoretic constructions for very specific degrees, which are explicit, which are some specific Cayley graphs, which give you big families of extremely good expanders, but we don't really know that many of them. And those come from arithmetic constructions which prescribe some specific degrees. So they're not true for every degree. And it's actually really difficult to come up with some examples. And we still don't know any example for every degree to this day. However, we know really, really well nowadays what the spectrum typically looks like. So if I take a random graph, random deregular graph of large size, we know that the spectrum will look like this, which is a rescaled version of the image on the right earlier. So what we know from the ATs is that there is a density here, which is actually the density from the infinite regular tree, which is the big infinite graph that's kind of overlooking the general situation. So you have this density, which is an explicit function called the Kessen-McKay distribution. What's noticeable is that it vanishes here at the edges of the interval where the spectrum is defined. And actually related to this vanishing here, Allen showed that any big graph, not random really, any big graph must have some eigenvalues around here at the beginning of the support of this density. Because the graph is big, it will have to get some eigenvalues from the tree. So that tells you that the gap between this first eigenvalue and the next one has a maximum value. It cannot be made arbitrarily large. If you take bit graphs, the most expanded they can possibly be is the distance between D and this point here, which is 2 square root of D minus 1. So Alan, following this observation, conjectured actually, which is quite surprising, to be honest, quite optimistic, that most regular graphs are almost optimal expanders. So he thought that if I take a random graph, it's going to have the best possible spectral gap up to epsilon. So in a sense, it's going to be very, very, very well connected, as well connected as it could possibly be. And this was a very exciting conjecture. A lot of people were working on it. And it wasn't proven until almost 20 years later, where Joel Freeman did a proof of this result, a much awaited proof, which was really scrapping the limits of what the field was able to do. So this is like 250 pages of very hard computations. And I would say that I'm not certain that that many people have read the entire proof. We have with my collaborator, but it was really exhausting all the tools available there, and a very impressive achievement from Joel Freeman. And after this, actually, 15 years pass and no one else is able to prove it using different techniques or new insights until 15 years afterwards. The last two articles on this timeline have a little star because of their preference. And that is to show to you that this field might look a little bit old, but actually a lot has been happening even in the last few years. So we know that the first eigenvalue is going to be around this point, but it might be slightly above or slightly under. And a lot of people were wondering, since Friedman's time actually, what's the proportion of graphs which have exactly their first eigenvalue under rather than above. And it was proven last year that around 69% of large regular graphs are exactly optimal instead of epsilon optimal. Additionally, this team has introduced a new method called the polynomial method, which allows to prove Friedman's theorem in 10 pages using only elementary tools from a very soft analysis. This has been a gigantic breakthrough in my field and has been having many, many consequences, which I don't think we've seen the end of. Okay, so this is me showing to you what a typical graph looks like. And now we'll go back to the question of understanding typical surfaces. Okay, so remember, we want to study large hyperbolic surfaces. So now imagine I lock you in a room with a pen and you're not allowed to go out the room until you've drawn me a large genus hyperbolic surface. I think most of you will draw this because you want to put a lot of genus, so you put them one next to the other. And this surface is very heavily studied. So examples constructed like this, we know many things about them because they're quite natural thing to think of. They're actually a little bit like the cyclic graph I had drawn before. They're examples which are easy to come by, but actually don't happen in real life. And that's what I'm going to talk to you about now. So this surface is not very well connected. So the same objects as the ones I talked to you about graphs also exist here. I can wonder about the diameter, so the distance between the two furthest away points. And here, clearly, the diameter is linear in the genus. I could even, thanks to hyperbolic geometry, I could even make it as big as arbitrarily large, actually. There's also an interesting operator to study. So instead of the adjacency matrix here, we study the Laplacian. And it also has a spectral gap, lambda1. And this one decays in 1/g. And the reason for that is that I can cut the surface in the middle using a fixed number of length with my scissors. So I'll have to cut a length 1 curve. And I cut my surface into 2 huge areas. And because of Cheeger, constant stuff like that, because of the links with connectivity, we can see that the spectral gap is 1/g. So both of these indicate that this surface is very poorly connected. And the quantities here behave in the same way as the quantities for the cyclic graph. Similarly, probably even worse than for graphs, we don't really know explicit constructions of compact hyperbolic surfaces which are very well connected, especially in the hygienous limits. In order to do this, a bit like Erdős, but I guess 50 years later, we say, let's take random surfaces. And this is a very, very good idea, a priori. So let's take all the hyperbolic surfaces of genus G in a big bag, take one and look at it and see what we get. The same way we did for the graphs, right? For the graphs, I just need to write one line in Python and I get my graph. Very convenient. Here, not so easy to do, because what does it mean? I don't have a finite set of possibilities, so I can't put like the uniform measure or define my random graphs as easily, my random surfaces as easily as I would define random graphs. So I'm going to tell you a little bit about the case of flat tori, because then I can draw pictures. So I want to tell you a bit what this bag looks like, the bag with all the hyperbolic surfaces of genus G. I'm going to show you the bag of all the flat tori first, and then we can talk about the bag of hyperbolic surfaces of genus G. So remember my flat torus, which I got from this square. Actually, as I mentioned, I could have gotten any parallelogram to create my flat torus. And then up to like shifting things around, rotating, rescaling, everything, I can assume one of the sides is 0, 1 on the, and that I'm drawing my parallelogram on the upper half plane. And then I just need to decide what tau is, what my little, I just need to pick another vertex of my parallelogram, which I'm going to call tau. And here tau lives in the complex upper half plane. So that gives me a space of flat tori. For every parallelogram like this, I can identify the opposite edges, glue them, I get a flat torus, except it's a bit too big a space, because a lot of these tori are actually the same. So I brought you another one of these, which is the one you get from 1 plus I. So this is exactly this one. And what I can do from this torus is I can take my scissors and cut it vertically up. And then I can move this one, put it back here, and I get back to my square, my initial square. So actually, if I start from this and identify the opposite edges, it's the same as if I started from here and identified the opposite edges. So if my space, if I was taking every possible value of tau, I would get many, many copies of the same torus. I don't want to do that. So instead of doing that, what we're going to do is we're going to say, well, if two tori are the same, we identify them. So we take the quotient of the space of tau, so the upper half plane, by the group of isometries. So here, magically, we know very well what's going to happen. You don't really need to understand any of this for the rest of the talk, but the identifications are encoded by matrices with coefficients in Z. And what's beautiful here is that there is a fundamental domain. That is to say, I have this little blue area here. And if I take tau in this little blue area, I see one and only one example of each flat torus that exists. So if I want to take a random flat torus, I can just take a random point of this very explicit shape in the upper half plane. Funny enough, it's almost kind of a hyperbolic surface. So here the edges, the opposite edges are glued together, and also this part is glued together while folding. So if you glue everything, you get something like this. Which looks a bit funny. So there's these two conical points, and then there's an infinity direction, which corresponds to going up here. But all in all, what you need to think and remember from this example is that we have a very explicit description of the space of all tori. And we can even here view it as a hyperbolic orbifold here because there's these wonky points here. But we have a very natural probability model and a way to sample a random point on here. Everything is very explicit. So that means I can study random tori using this approach. I can really take the bag of all tori and very naturally consider a probability measure on it. And everything is very beautiful and explicit. Okay. What happens now in dimension G is very similar, actually. So I was using my little square or my little parallelogram as construction pieces. In hyperbolic geometry, we have different construction pieces. Normally, I bring an actual trousers from my daughter's doll, but I forgot it today, unfortunately. But the construction pieces we use in hyperbolic geometries are called pairs of pants because they are like trousers, so they have a belt and two ankles. And what's beautiful about them is that if you give me any three numbers, there is one and only one such pair of pants. So the same way as you know entirely what I mean if I say I'm taking the square of sides 1003. Here, if I tell you the pair of pants has sides 1, 1.6, and 3.8, there is one and only one, and I can just take it. And this is amazing because you give me three numbers, you get a little hyperbolic surface. Now you can glue them together. So if you want to construct a hyperbolic surface, you can always glue 2G minus 2 pairs of pants. If you want to, so by gluing, I mean really like sewing together the two ankles, for instance, with my little sewing machine. So I need them to be the same length, otherwise they won't glue it properly. So for every edge here, I will need to take one length, which is the length. However, when I glue together, say, two trousers along the belt, I need to decide whether or not to line up the buttons. Do I line them up? Do I twist them a bit? And then once I start sewing, everything comes together. But I have 1 degree of freedom upon starting to glue things together, which is called the twist angle. So all in all, what I'm saying is that I can describe any hyperbolic surface by picking a certain set of coordinates, those lengths and twists, which are called French and Nielsen coordinates. So that tells me that my bag, the space of surfaces, is something like looks like very simple. So it's a power of R, basically, divided by a discrete group. Because once again, like in the case of tori, a lot of them are the same. So I don't want to take the whole space here. I need to take a portion. So that all looks really nice. And actually, you can prove that there's the Lebesgue measure, basically, on this space is a nice measure. And it's finite, so you can get a good probability. It should be noted that up to here, everything is known as to the 80s. So it looks like we could just study that. And well, I think there's an element that people did not care about probabilities. People in pure maths did not care about probabilities at this point. So perhaps that's one of the reasons why people haven't really studied this model. But actually, there is a very, very, very difficult blockage at this point, which is that we don't know any fundamental domain. So in the previous example, I knew this very explicit place, and I could tell you, well, take a random point here. And that's what it means to take a random torus. Here, we cannot do that. We do not know how to do that. And that means we just cannot a priori do anything with this model. It's a bit silly. We know that the space is Rn for some n, but we don't know on which subdomain of it to integrate. So we just don't know how to take a point. So it's quite like sad. And that's just been a complete blockage in the field, a very big technical challenge. So a good approach to remedy this is to instead think of another bag, another way to sample surfaces. And people have successfully introduced a variety of combinatorial models, which are more like hands-on, so not studying the whole bag, but rather a little model of them. One of the models consists in gluing some triangles following a random graph. So actually, the geometry of the surface you obtain this way will look a lot like the geometry of the graph that you took in the first place. And this is the historical model of random hyperbolic surfaces that's been first studied. And the surfaces you find this way are very well connected, and they form a dense subset of the space of surfaces. So we now know that in our bag, there's a dense set of very well connected examples. And this is really a really beautiful construction, which actually has other relationship, a more algebraic side. Another very good idea has been introduced more recently, is to start with one surface, which I know, for instance, the Bolzan surface, the one with the octagon I showed you at the beginning. And then to wonder, I pick a degree. So here is 2 on my picture for simplicity, but I will pick a high degree. And I take covers of my fixed surface uniformly at random. There's a finite number of possibilities, and I can take one uniformly at random. This actually raises very interesting question of the representation theory of free groups and surface groups, and has been a very exciting area of mathematics in the last few years also. Another construction is actually very similar to the first one, but you take pairs of points instead of triangles. And this construction yields examples which are a little bit of a different flavor somehow. However, they are the first and only example that I know of surfaces of minimal diameter. We know that the diameter is always at least log g. And in this example, you can construct examples, not explicitly, probabilistically, of diameter log g. Not 2 log g, no, not 3, log g. So these prove the existence of surfaces of minimal diameter. It's a funny situation here. We don't know any examples, but we know that it's true with probability 1 in this model, so it must exist. A lot of the things I'm talking about right now, we know they exist with probability 1, but we don't know any examples, which is quite interesting to me. Okay, so these are all beautiful models. However, what I work on mostly is the fact that are the consequences of several breakthroughs by Maryam Mirzakhani in the 2010s, which allowed to integrate functions on my big bag. So now I still don't know a fundamental domain, so I still don't really know how to describe the space I'm working on. However, somehow, thanks to several different very smart IDEs, which came together very beautifully, I can actually compute probabilities on this space, even though I don't know how to describe it so well. So there's this sequence of papers. This last paper defined all the tools and gave a lot of first insights as to the geometry of these surfaces. And after that, there's a very long break. And then in the last few years, it's just completely exploded. So when I started my PhD, that's the only paper in the field. And now there's, I think I counted 30 last time I counted, and that was a while back. So probably more like 40, 50. That's quite rare in pure maths. So very excited. Okay, so what do we know now? Well, I can plot to you a bit like before for graphs, the spectrum of the Laplacian this time. So the Laplacian has always 0 as its first eigenvalue, and then there's an increasing sequence of eigenvalues, and the second one is strictly positive. And what we know is a bit like the density that was for graphs before. There is this density, the one of the hyperbolic plane here, which is an explicit formula given by Selberg's trace formula. And we know that if I were to take at random a hyperbolic surface of large genus, its spectrum would look like that. With a big caveat, because this is a bit of a misleading image, I am not able to tell Python take a random hyperbolic surface and compute its spectrum. At the moment, I don't know anyone who can do that. So this is me plotting things a bit just for the purpose of illustration. And unfortunately, we don't know how to make an actual numerical picture of this. However, morally speaking, the spectrum should look like this. So there is the trivial eigenvalue here, and then there's a gap. And then there's this density, which starts very sharply here. So now so that's the first result, is that we are well approximated by this density. And then for the rest of the talk, I'm going to talk about this gap here, which, remember, measures how well connected the surface is. So there's a very quite similar timeline, but a bit of an accelerated story towards the end. Bruiser actually conjectured, or actually said probably that probably there's large hyperbolic surfaces of optimal gap. So actually on the same, almost the same year, Alan said, oh, most regular graphs are near optimal expanders. And Bruiser said, well, probably there exists some optimal expanders. And until 2013, we knew nothing. However, in 2013, Mirzakhani showed a very small but fixed lower bound on λ1, which was actually a very impressive achievement, and an upper bound on the diameter, which is logarithmic. So that tells you that typical surfaces are well connected, not optimally, but already quite well connected. And then Hyde and McGee, using the random cover model, proved the existence of optimally connected surfaces. So they answered positively to Bruiser's question 40 years later. So from their paper, we know that there exist surfaces which are near optimal expanders, extremely well connected. But these are not constructed. They are probabilities constructions. We have proved in all the different models now this year, so here those are preprints, that typical surfaces are near optimal expanders, so they satisfy λ1 bigger than 1/4 minus epsilon, with epsilon as small as we want. And we also have a bound on the diameter, which is non-optimal because these two could possibly be a 1. And so this is for the model I was describing, this big bag of surfaces, but it has been extended to all the other models that we know of during this year. The methods for these, and also for this improvement of our result, has been to use these polynomial method, which I mentioned for graphs, which, as is illustrated here, led to a lot of new developments. The question for the future is to prove optimal expanders. So remove this epsilon here, which for graphs took 20 years from when we are now. I used to think it would be in a long time, but now actually so much has happened, I don't know, maybe sooner than I'd thought. So the question would be, can you show that the limit of the probability that lambda is bigger than 1 is a number strictly between 0 and 1? In particular, that would show existence. And probably these questions are related to questions in random matrix theory. So yeah. Thank you for your attention. To take back with you, so this is my little cyclic example, and this is me trying very hard but failing to draw what I imagine. So this is really not what a typical surface would look like, because there's a lot of small bottlenecks which actually won't happen, but to show you that you can do much more well connected than this already. Thank you.
Well, thank you very much, Laura, for a really brilliant lecture. Are there any questions for Laura? Well, do we need a microphone for the question? Right there in the third row, sorry. Could you just raise your hand so that we know where the microphone is? Yeah, great.
My question was about hyperbolic 3 manifold. It seems like the sort of things you presented would not straightforwardly carry over. Is there something, can you explain what is special to dimension 2 that that would prevent you from studying, say, random hyperbolic surfaces and random hyperbolic 3 manifold? So
that's a very good question. So we have a rigidity result which tells you that after dimension 3, included 3, if I fix a topology and I take this bag, there's 0, 1 thing in it. So I can't fix a topology and then vary the metric anymore. So then I need to think about other ways. And so I need to take a random topology kind of. There are ways to do that. One of the models emulates the triangle model where you glue some tetrahedrons, but there's not a natural space of all metrics that you can vary the way we can vary here. So it's a very big challenge, also because we understand them a lot less. So thank you.
Any other questions? If that's not the case, then let's thank Laura again.